This material isn't something that you'll directly use in your robot, but it's very useful in your engineering career in general for your own projects. And there's a chance some of this could be useful, at least in terms of doing the layout, schematic entry and layout. So this lecture is a combination of sort of overview of very, very brief circuit board design, as much as I can do in an hour, in combination with the tutorial. In the lab today, it's entirely an optional lab, so if you want to do a circuit board design, the lab time right now, the TA should be there, so if you need help. Otherwise, you can do it later. And the only deadline is that next week, if you want to get your board physically manufactured, you need the file in next Monday by 1 p.m. type thing, because Mark's got to package them out and send them out to the fab. So that's the only deadline. There's no marks associated with this at all. It's purely for your own use, and it is quite useful, and you end up with something you can keep, so it could be interesting. So I'm going to be covering a little bit about, as I mentioned, the background, as what they are, some of the nomenclature you're going to see, how we design them in one piece of software that we use here, Eagle. You can use other software too, how to order them, and a little bit on ordering components if you haven't done this before. All right, so printed circuit boards. Printed circuit boards is sort of the progression of when we're doing electronics design. The most basic thing we can do is breadboarding. So you've already used breadboards, and here we have the chips that are connected through these temporary wires to form the electrical connections. And this is fine. There's a few issues with it. Number one is reliability. If you're trying to mount this somewhere that's going to vibrate, these wires could fall out. They could just be knocked out. You can get oxidation on the contacts. The second problem is that a lot of components no longer fit into breadboard. So if you look at what are called surface mount devices, which are really small parts with the leads coming out of it, there's no way to easily mount them. You've got to mount it on another circuit board and put them in that. And another issue is if you start doing high speed or analog circuitry, it can be more difficult or very difficult to get sufficient performance out of a breadboard. Very similar to a breadboard though, and this is sort of an older technology, is something called wire wrapping. So it's hard to see here, but this is the backside of a large wire wrapped board. And what you have is, you can sort of see these pins here. And each of these pins, can have a wire wrapped around it, and then it goes to some other pin there. So this is before the advent of really low cost and easy printed circuit boards. This is how whole, computer systems were built, is this wire wrapping. So you would have to, make sure you did the right connection, because it's going to be very difficult to trace that afterwards. So instead of that, when you go to design, you say, okay, I've done some breadboarding, I've got a pretty good idea this is going to work, and I'm going to lay out a circuit board. And you can do a board, a fairly basic board like this. So this is a combination of through-hole parts. We see like connectors at the edges here. Surface mount is what I mentioned. So these parts are ones, I should switch color, are ones that would not fit in a breadboard because they don't actually physically have leads that go down anywhere. So you can sort of see this outline here. There's no holes here. So the part itself solders right on that. And we might have stuff like there's a switching power supply that would be hard to breadboard because of the current that it's going to be passing through. Wouldn't work very well on the breadboard traces and some other issues. So these type of boards you can actually do really cheaply and easily nowadays. And so it's something that as you sort of have interest in electronics and go to build projects, it's a very useful skill to have. So some of the features when we look at this board, what you see is that the board itself is this raw copper, and the copper has been etched. So you can see here, this copper has been coated with something. In this case, it's coated with solder, and you can sort of see how it's connected based on the color difference. So all of these lighter sections are connected together. And then when you see the darker sections, that's where there is no copper and there's no electrical connection. So to protect the raw copper, so there's no electrical connection there in these sections. So to protect the copper, over top of it we put what's called a solder mask. And this covers areas that we don't want solder to flow. It electrically isolates the raw copper from anything. So So these areas there, we could scrape it away. It's just a thin coating like varnish or paint or something. You can use a knife and scrape it away, and it's just raw copper underneath that. The other thing we see is Silkscreen. So the purple, or not purple, the white text here that I highlighted in purple is what's known as the Silkscreen. So this is just some sort of, it's all non-conductive. And when you go to assemble the board, it tells you, there's a capacitor labeled C7 that goes right here. So I know to put a capacitor that's C7 here, or you can see a number of the pin here. So if I'm counting pins, or somewhat crushed in here, the Silkscreen's a little crowded right there. It's marking where pin 1 of this IC is, so I know which way to put it. So the Silkscreen is just whatever text. Normally it's stuff like that, but you can add, you can put a label if you want. You can write something. You can make a little graphic. So that's what the Silkscreen layer is. If we look, this is looking into the side of the PCB. What we see is that for a PCB with a certain number of layers, this is what's known as a 2-layer PCB. So there's copper here, copper top, and copper bottom. So it's a board, there's copper on both sides, and that copper can be connected by what's known as a via. So a via is a hole that goes through that can electrically connect 2 traces. So looking back at this example here, let's see, is there a good example of a via? All of these, so these holes here are vias, and what they're doing is if we were to flip the board over on the other side, so this is a via here, and there's a whole bunch you'll see elsewhere on the board. Those are quite large ones. This is a via. There's some smaller ones here. And what you can see is that these traces, for example, this trace here seems to end. It goes to this spot, and then there's nothing. And that's because the via has brought the trace onto the other side of the circuit board, and you can continue writing it. So when we look at what's known as the stack up of the board, those names I used before appear again. So the Silkscreen is this very top layer, and this again was just whatever material I wanted to write about the circuit board on it. The solder mask is put right on top of that conductive top layer, which is copper, normally coated with something, so it's either immersion gold coated, or coated with tin, or coated with solder, which could be lead or lead-free, depending. So some sort of top coating on top of the copper. The only reason we do that is copper will oxidize, which we don't want if the boards are going to be stored for a while. In between the 2 copper layers, so the top and bottom, we have this dielectric layer, or what's known as prepreg often. So this is a combination of epoxy and some other material often. It's effectively like the fibrous weave with epoxy stacked in it type thing. So it's just some sort of electrically insulating material. For more expensive boards, you can get different materials here that work up to very high frequencies and stuff like that. And the bottom, so you see the bottom is more or less just a mirror. We again have a solder mask on the bottom and a Silkscreen on the bottom. If you do a very cheap board, or if you get PCBs made by Mark, they're capable of making some simple boards. They won't have these top layers because they're more complicated to add, so you may just get pure copper, and that's all you have. You don't have the fancy boards. But when we order them from an online service, you'll get everything. So you get the solder mask and the Silkscreen, which is nice. So the basic process of how you end up with this circuit board is you're always going to need the schematic first. So you're going to prototype the design. Based on your schematics, you do the design, do the prototype. Once the prototype sort of works, you might lay out your circuit board and send it away, have it made. So this can take, depending how much you want to pay, if you pay a lot of money, you can get them within 24 hours of submitting them. If you don't pay a lot of money, it could take 5 or 6 weeks before you get them back. It just depends what your budget is and stuff like that. You would then assemble it and check the design works. Almost always, your first revision, unless it's a fairly simple board or you've spent a long time verifying it, will have some sort of errors. Hopefully not too big of errors, and you can fix them with some wire So then you'll make revisions, and you sort of go back to here, fix it up, have it made again, build a new one, check if it works. Hopefully within 2 or maybe 3 revisions, you'll have everything sorted out. So when you do the layout, besides obviously saying, okay, what parts are we using, what's the package, how are we going to lay them out, one of the things you have to be aware of is what's known as design for manufacturing or manufacturability. As part of this, there's a number of rules you'll have to perform, which will be called the design rule check. And basically, you need to confirm that the PCB manufacturer only has some ability. For example, there's these traces. You can only make these traces so thin. If they get too thin, what's going to happen? Oops. If they get too thin, they may have electrical breaks in them. So there's going to be a thickness of the trace, and there's also a spacing. So what's the space between 2 copper features? If you bring them too close together, they may short out. So that's normally what's known as the trace in space. And you'll see stuff written like 7 mil. Commonly it will have something like 7 mil, 8 mil, 6 mil. What this means, and when you see 7 mil, it just means 0.007 inches is the minimum trace in space that you can get away with. You always want to be above that if you can. So if you have a very simple layout like something like this, even if your circuit board manufacturer can make stuff smaller successfully, you want to stay, okay, well, they can go down to 5 mil, I'm going to stay at 7 mil because that's all I need for this design. I don't need to go to a very dense layout or use very thin traces. Obviously, very thin traces can't handle as much current as a thicker trace, so unless you desperately need the thin trace, I tend to stick with thicker ones. If you're doing power supplies or something like that, you need to consider what's the actual minimum thickness to carry the current. There's also issues like what size drill can they use. So looking at this board, these here are actually drills. These are vias. They've been covered over with solder mask, so that's why they don't look like open holes. But there's a minimum size that they can drill. So you've got to ask them what's the smallest drill you have. So that's something. And there may be other considerations like how thick. So you can see the silkscreen material here. You can see it's sort of looking, a little bit dotty. It's not too bad. But as I try to make this text smaller and smaller, I'm going to lose the resolution, and it can no longer print that on the board. Or you can see this silk screen right here. You notice how it's broken in spots. Maybe my line was a little too thin, and what's happened is the circuit board manufacturers tried to make it as is, but I specified, let me highlight that better. I specified too thin a line, or the line was too close. I think what happened here is the line was too close to these copper features, and so they've actually scaled it back a bit to say we don't want this line to go over your copper pad, so we've moved it away from the copper pads, which gives you this broken line. So there's all sorts of considerations like that. So that's the main things. And doing that check is called the design rule check, the DRC, to confirm. So when you have your circuit board, you'll confirm that all these measurements are okay, and the tools will automatically do that. If you're going on to manufacture the design, there's going to be other considerations, like how do we ensure the pick and place machine is able to find parts. So what this means is that if I go back to my whole circuit board, there's automated systems that will basically pick up parts and simply place them blue here. So it'll place like ICs that go here and stuff like that. It's effectively robots that pick up the parts and just place them down right on your board. So there's some considerations if you go to using higher volume, or even for low volume, you can use this. How do you ensure the device is able to orient your circuit board in the system? So it will require some changes in your optics. You need some marks to indicate what's the reference point on my board. So for the stuff you do, you don't really care about that. It might be useful to consider it in the future, just so you're aware. And what those machines look like out of interest. So they go very, very fast. Here's one I was using. Connect to the network. There we go. So this was a video I took of a board I was having assembled just in Dartmouth here at a company called Suncell. So you can do this have this done locally. And what you'll see is that the a circuit board is going to come in on the left side of the machine. Is coming in on the left side of the machine, and there's this large head here. This is all in real time. Is going to go ahead and pick up parts and then place them all over the machine. So let's apparently the Dalhousie network. Yeah, not the fastest. Normally it's better. I don't know why. Okay, there we go. Yeah, so you can see the circuit board coming in on the left is being loaded into the machine. Oh, come on. What the heck? I'm just going to let it load a second. So you'll see this head. It has a whole bunch of, you can see some of the numbers there, 25, 26, etc. Those are actually pick and place heads, so they're little vacuum nozzles effectively. You can see the tiny nozzles there. Over here, there's a whole bunch of what are known as feeders. So this just has a whole bunch of parts set up. So it'll just go along, pick up parts, and then put them down on the board. And it takes, like, you'll see 30 seconds. It's building 4 at a time. So it's just going along, picking up, 20 parts or so. And then you can see it just shoving it down right on the board.
This is real time?
This is real time, yeah. So, and for each part, you can sort of see the flashes with the camera. The camera fell over there. With the camera sync, you don't see it perfectly, but those flashes it's imaging each part as it picks it up to check the orientation, check it's the correct part, and figure out, how much to rotate it to put it down on the board at the right part. So it runs very, very fast. This is a fairly high-speed machine.
This is done in those places?
Yeah, this is in Dartmouth at a place called Suncell. So they have a few different machines. You can get lower cost versions of this too, but it's all the same idea. But so that's if you go to higher volume stuff, there's additional considerations there. But we'll go over. But anyway, so the other thing you'll need to know about is, so you have you have a design, you want to get it manufactured. How do you do that? You'll see everywhere this reference to Gerber files, and so this is just a very a historic file format that's been used in circuit board layout, but it's still in very widespread use, and this is what most of your designs will end up being submitted in. And basically, it's this universal format, and it was originally designed for use when, if you were making the board, how you had it is you had this light source, and this light source could pass through what is known as one of several apertures. And these were just a certain diameter, like a 1 millimeter circle or a square of 2 millimeters or something like that. And it would literally expose this aperture onto a photographic film, and it could move the aperture around. So you can draw is what you're doing basically. So if you look back at a circuit board, it could say, expose this as one item, and then switch to a round aperture, and simply drag that aperture along to draw this whole trace. So this is still the file format that's used to send the data to your manufacturer. And what you'll see, so you'll see a few different names for it. Because it's a historic format, there's been different revisions. This RS274X is what almost everyone's using. If they say Gerber, that's what they mean, is that format, normally. Officially, it will be called the extended Gerber format because it's more recent. Very, very few people would use the original for standard submissions. So we'll see how to generate these files from your design software as part of the very quick tutorial. The other, so that's what most of your file is. There's one other type of file you need, and this is a file that has the location of the drill. So it says where, all these drills, these holes in the board, you can see them here in the diagram. Where do you want these drilled, and what size hole should we drill? So this is what's known as the numerically controlled drill file, or NC file. It's also going to be occasionally called the Epsilon format. And this is after the company that originally pioneered a lot of these machines, and I believe sort of used this file format that became the standard. But officially, or normally it's called the NC drill format, so you'll see that referenced. Submit your Gerber files in NC drill. There is, because these are fairly historic files, there's a lot of different options about, are we talking about a millimeter file? Are we talking about an inch file? What sort of decimal places? The numbers inside the file, if you open them up, just look like that. And what the system has to interpret that is do you mean, 2.427 millimeters? So this extra stuff is not in the file itself and is part of sort of what's specified. So the decimal place and the units is not actually part of the normal file format. Officially, you would have to specify, what is the file format. Most of the time, this can all be the PCB fab or your viewer software is able to interpret this for you, so you don't have to specify exactly what it is, but occasionally you run into issues. So just as a warning, there's no universal. When you just say Gerber, it actually could not only mean a few different formats, there could be variants within the format. So you shouldn't run into that, but you could. And to generate them, it's entirely from your design software. So I'll show you how to do this from Eagle. If there's other design software, you may have different options that you can use. But and once you have them, it's a universal format again, so you can use a viewer to check the files look right. Two options I like. So the first one is this Gerb, and basically it's an open source project, and you can get viewers for I think any Windows, Mac, Linux, whatever. And it lets you view each layer. So, this is going to be the top copper. This is going to be the Silkscreen. There's another one I like here that mostly works. It's a 3D viewer, so you can sort of preview what the circuit board will look like. It's not quite as reliable, so sometimes it won't read the files if it's complicated or it has issues with the format. But when it works, it looks really nice, and you can use it sort of for a few of the layers. I'll show you that too quickly. All right, so if you want to do the lab today, what we're going to be talking about is CADSoft Eagle, which is a schematic and PCB layout software. You can get a free version of it for basically if you're not using it for commercial work. They have some two free versions of it. If you just download it, there's a more limited license. If you register on the website, it's still free. You get an extended license that gives you some additional features. So some of them, it depends. So things like multisim, some will just be schematic entry. So I think that maybe, I knew they had a PCB layout add-on to it, but they'll only do schematic entry is one thing. There is other tools, so like Altium, and Altium used to make a very high-end tool that it was around $7,000 a year for the license. They recently released, I think, Circuit Maker, it's called maybe, which is a free, it's sort of web-based. I haven't tried it yet. So Eagle's far from the only one option. They use this a lot at school, so that's the only reason.
Is this one just the most accessible one?
Yeah, right now it's probably the most accessible to you, I'd say. It's nice because it's free. If you want to buy a commercial license, it's not that expensive comparatively. It's, depending on what size you get, like a few $100s and up. Compared to Altium, that's like 7,000. So if you have a design and you say, hey, I want to actually sell this, it's pretty reasonable to take it to the next step with Eagle. So I like it for that reason. I've personally used it for a long time, so I lean towards it. But it is far from the only option. You can download, almost all of them have trials, so you can download and play with them. The one thing we'll see with Eagle, some of the user interface is a little crazy. It's an older program. It had some weird nomenclature in it for a long time that's only recently been fixed. So some of that still survives. And this is going to be a very, very fast tutorial. So there's some more. Eagle itself comes with this, both the manual has a tutorial in it and a tutorial file that goes through a whole bunch of features. There's a SparkFun tutorial that's more in depth than what I'm going to show you, but still fairly easy. So it says how do you make a schematic, make a board, and stuff like that. So this will give you sort of an overview of the whole thing. You might need to see some more references to really use it. If you want to do the PCB lab and have it manufactured by Mark, so they'll send it away for free for you, you have to use Eagle because they have to take your Eagle board file and modify it a bit to fit them all, to have them all made. They can't use other formats, so that's the only restriction here. But for your own projects, you can use whatever software. So I'm going to go through the steps and then actually use Eagle sort of in the background here. I'll see how this works. So Eagle itself, this is sort of what the main window looks like. So we're going to start Eagle, and you can create a new project. So let's do that. So I have Eagle running here, and I can just delete this old. I'll delete the existing project. So I'm going to say, make a new project, and just give it a name. Lecture demo. You can then make a new schematic. So I'll say new schematic, and it'll open the schematic. So you might want to save it right away. By default, it doesn't save it, so I'll just save it as demo. So there we go. So you get this big blank sheet. So some of the first things to do is you can add a frame. So if you print it, this will print on a standard letter size sheet. You don't have to add this. You may end up wanting a huge schematic, depending on your license, if you can't have more pages. I'm just going to add this for now. So to do this, there's a command toolbar at the top. And what we're going to do is we're going to type a command in here. So this is actually adding a specific type of part. But I'm going to type add letter _ L. So this adds a landscape frame. And you can see you can stick it down somewhere. So you'll see very faintly a crosshair in the corner. I'm going to align with that crosshair and then hit escape. And it now has added this frame to the schematic page. And if you hit zoom to fit, you can sort of see the whole thing. And I'll save it there. All right, so the next step is to add a part. So there's a little add parts icon here on the side. Depending on which version of Eagle you use, it might look a little different, but it'll be something like that. Looks like a little gate with a plus. When you hit this, it's going to pull up a huge list of possible parts. So basically, you can go through different libraries. The libraries are pre-made sort of bundles of parts, including the schematic symbol and the circuit board layout. And it shows you both. So you can see here, this is what the schematic symbol looks like for this resistor I want to add. And it also shows you what the circuit board, when you go to design that, will look like. And there's a bit of a scale at the bottom for the circuit board. So something as simple, the only sort of confusing thing is there can be a lot of variance. So like just adding a resistor, the easiest thing you can imagine, you first have to realize that it's called the RCL library, which is resistor, capacitor, and inductor. When you open that, it gives you all these options. And next you have to realize what I want is R-US. So this is the US resistor notation. Basically in the schematic, you have two options. In the US or really North America, we tend to use the resistor as a squiggle. In Europe, a resistor is normally represented as a square box like that. So you can use either. We'll use the US notation because that's more common here. And finally, once you expand that, you'll have like 100 different options for the physical package. So you'll see all these options for the resistor. And what you'll sort of see is that these options are representing the size of the resistor. Resistors comes in tons and tons of sizes. The standard one you have, which is like this 1/4 watt size, is about 2 millimeters wide and the holes are about 10 millimeters apart in the circuit board. So we can do that. So I'm going to hit the Add Part button here. Again, we get all these libraries, or scroll down to RCL, resistor, capacitor, inductor. I'm going to select the US symbol and expand it, and then you can see all these options for the packages. And if I go 0207/10, so we can sort of see what the circuit board layout looks like, and you could measure, that's about 10 millimeters between the holes. There is other options, so you could have something like, well, I want it to mount vertically. I want it to sort of be a U on the circuit board, so we could use a different package. And you can change the package once you've done the schematic. But I'm going to do that and just put like 4 down. Like that. The next thing we want is we want like a 5-pin header. We're just going to make a really simple board, so we can search for parts by adding a star, basically to do a wildcard search, just like any other search engine or something like that. So when I do the add part, I'm going to, in the bottom here, this little search box, I'm just going to type star header and then star afterwards. So this will match any text before header and after header, and it's going to search anywhere. So in the description, in the name, anything like that. And what you'll see, you'll get a whole bunch of matches. Just close the magnifier. So you'll get a whole bunch of matches, and you can just sort of scroll down to see what's a reasonable thing. In this case, I know there's a library called pin header here, and this just has sort of generic pin headers, like if I have a 5-pin header here. So I'm going to have something like that. You can see there's various options if I wanted a right angle pin header. And you have to be careful. In this case, that 2 millimeter is a smaller spacing than you would normally use, so you don't want that. You want something like this. And one of the things you'll end up having to do before you make a board, you print it out on a piece of paper, life size, and you can check all your parts actually fit so that you've gotten the right footprints. And if I right click, you can see it rotates. So I'll rotate this way. Oops. All right, so the next thing to do is make electrical connections. Now here's, again, when I say the Eagle UI has some crazy stuff going on. If you were making electrical connections, one of the classic beginner mistakes is to say, oh great, there's a wire tool. I want to wire up these pins. And that's completely wrong. If you use the wire tool, it will not work at all. The wire tool is only for drawing lines on the schematic. So if you want to say, oh, all these parts are part of one block, no electrical connection, you could use the wire tool for that. Instead, you have to use this net tool. And this net tool is actually making electrical connections. And I'll sort of show you how you confirm that.
Are we having only 1 layer or 2 layers?
We'll have 2 layers on this.
Okay.
So if you want. So when you do the lab, by the way, I'm just doing a really simple schematic. You can make anything. Ideally do something useful, so you don't have to necessarily finish this today. But I'm doing a really simple example here. So I'll draw an electrical connection, and you can zoom in with the scroll wheel. And because I'm using the net tool, you want to make sure you click on what's the actual pin. So here I clicked on that one point, and we'll check afterwards that we have everything connected, and I'll just connect together. So if I miss, for example, that one did not hit the pin, we'll be able to detect that afterwards. And there's sort of 2 ways to do that. And the other thing you can do is if you go too far, it also won't make an electrical connection. So if I drop it there, so the 2 ways we can check that everything is connected. One, if you move a part, you'll see that everything that's electrically connected should rubber band like that. Anything that's not won't rubber band. So you can see that one's fine. This R4 here, when I move it, you can see it didn't stretch that other wire. There's no electrical connection. The other way we can catch that is when we're done, we can use this, there's an errors flag here, which can do, I think it's one over maybe? Yeah, there's this ERC electrical rule check. If we run this, all it's gonna do is check that all the pins are connected to something. So you can see it's saying, hey, you overlapped a pin here, that's suspicious. You probably wanna check that. Or there's only one pin on this, this net, or there's an unconnected pin. So it tells you a few different possible errors. It's also flagged right now that I haven't assigned any values to any of these, so I can fix the, to fix the connection errors, all I'm gonna do is use the move tool and move this guy over, so now it makes connection. And I can move this net over, oops, and now it makes connection. All right, so that's easy. When you're using Eagle, note you can also type commands in that command bar. So that's what I did originally, that add letter underscore L. So I find it faster sometimes if you're doing value or move to just type it really quickly. You can add, if you know a part or you know a part of a string, you can add it just by searching right in that command bar. So it's all wired up using the net command. And the next thing I'm gonna do is add a value to the resistors. So the notation you use is sort of up to you. One thing I commonly use is, you notice I have the value of 2K2 here. So this is actually equal to 2.2K. The only reason I have 2K2 instead of 2.2K is that if you're glancing really quickly at a schematic, it can be easy to miss the decimal place and read that as 22K. So by putting 2K2, it's really obvious that, hey, no, this is supposed to be 2.2K. So this is another notation you'll see quite commonly in a lot of schematics. So you should sort of be familiar with it. So if we're talking about capacitors, you know, you might have 1 or 4 micro or 7. So this is a 4.7 microfarad capacitor in this case. And we don't put the F part just to make it a little cleaner. So if I put for U7, 4.7 microfarads. So to do this, we just use the value commands. Where's Eagle? So just say value, and then I can click on each resistor and assign it a value. Oops. So 2K2. Alternatively, I can just type a value in the command line and click on each resistor that I want to be 2K2. And it's going to assign it to that. So now I've assigned values to each of those resistors. All right, so I'd save the file, which I already did, so I'll just hit Control S again. And finally, we'll generate a circuit board from this schematic. And this is pretty easy. There's a button here, this Generate Switch to Board button. When you hit that, it's going to say, hey, there's no board already. Do you want to create one? And you just hit yes. And it's going to give you a default layout like this. So let's just do that. So I'm going to use this create from schematic button and then hit yes. So this is our default, our circuit board. The colors can vary. So in the previous slide, the colors, it was all black. Normally the background, I think, is all black. It shows up a little better with the white background, so that's the only reason it looks a bit different here. So the next thing to do, one critical warning, as you modify, so if I add a resistor in the schematic, it adds it to the PCB already. If you close one of them, that system breaks and it really screws up your files. If you close one, it's going to give you this warning bar here. So it's going to say this annotation was severed. So you just have to reopen either of the documents and that'll go away. So if you see this warning, proceed with caution. Make sure you have either closed both files or opened both files. So one of the things for your lab, if you want the board to be made, it must be a 40 by 40 millimeters, so 4 centimeters by 4 centimeters. If it's anything else, Mark isn't able to put a bunch of them together to get them manufactured, so your board might just be left out depending how much time he has. So I'll show you how to set out the outline of the board to be exactly 40 by 40 millimeters. So the easiest way to do this is we're going to use the grid command to set the grid to be in millimeters. By default, it's in inches, so we want everything in millimeters. And let me just switch the colors to be more common. So this is sort of probably what it looks like by default normally. So I'll change the grid command to be in millimeters. And then if I right click on one of these lines, so there's that faint outline is the board outline. And you'll see it tells you what is the location it's from and to. So these are just coordinates. Everything that's not 0, I'm just going to set to 40. So this is in the slide. It shows you it should be 40, 40, 40. The 1 is 0. And we'll do the same thing for this other line segment here. Set it to 40. And we end up with a nice 4 centimeter by 4 centimeter board. So this is what the size your board is allowed to be. If you want Mark to make them. If you don't care if he makes them, then it can be any size. And I'll show you how to use that later. All right, there we go. So again, we right-clicked on those lines and changed the coordinates to give us this outline. You can then move, so using the move command or typing move, you just move the parts to somewhere they look nice. That yellow line there, they're part of what's called the rat's nest or air wires. So they're just showing you that eventually you have to electrically connect this pin here to this pin here. And it's just doing a straight line. So they call the rat's nest generally, or air wire, and that's because rat's nest, if you ever find one, look really messy like that. So you're going to have to route the lines. The rat's nest itself is not, there is no actual connection. So you have to route the copper lines on your circuit board how you want them to go. And you can do this on the top or bottom layers, and you switch between layers with a via. So let's go back to our design. And first I'm going to move these parts over. So generally when you're looking at the rat's nest, you want to make it as clean as possible because that will make your routing easier. So for example, when I'm placing this part, I could place it like this, but notice all the lines are sort of crisscrossing. That's not ideal. So I might continue to rotate it and say, okay, that looks nicer because the lines aren't crisscrossing anymore. And similarly, when I'm placing parts, this is a valid placement, but it's nicer if it's down here. And that's because I know it will be easier for me to route this board once I actually do the routing in like 30 seconds here. So to do the routing, you enter the route tool and you just click on those air wires. And now you can actually put down where you want the copper to go. So the copper should connect those two lines. It's gonna show you. By default, it's using whatever the grid specification is. The grid says, how closely can we pack these lines. The default grid should be fine for this board, but if it's too coarse, you may need to reduce it if the jumps are too large. So let's do that. And actually, I'll show you, when you're in the routing tool, you can select to route on the top or bottom layer by default. And you'll also see there's different types of corners or routes to use. So it can either be square lines or on angles or any angle, 45 degree or stuff like that. You'll also have a choice of grid width. So in this case, the grid width will be in millimeters. You can switch the grid to be mils if you want, or something else. So 1.27, that's sort of like a reasonable, that's a pretty thick trace. By default, it's like 0.6 or something like that. The width of the trace will depend on the parts that you're routing to, how much current you need to consume, and stuff like that. We also have, if you place a via, so if you switch from the top to the bottom layer, there's the via drill size, and again, the size of the drill depends mostly on, the critical thing is you don't want to go smaller than your board house is able to make, so you just have to look up what's their minimum. But if it's a very high current trace, you don't want a tiny drill because it's just a tiny amount of plating material. So it will depend a bit on those considerations. All right, let's route this. And when you're in routing mode, I guess that's the other thing. So this is from the Eagle Help file. There's various, so if you right click, it's gonna switch between, if you do 45 degree or right angle or stuff like that. And you can do various things to reverse directions. To add a via, a useful one is if you hold the shift button and left click, it's gonna add a via wherever you are. So I'll show you that quickly. So here's our board. If I hit route, so if I click on this air wire here, you can see that there's that blue trace is now the copper. The blue is the bottom layer by default. So maybe I'm going to route this on the top. And I can choose, for example, to use a wider trace. So I could say, well, I want something like that. And when I right click, so you can see the trace style as I right click. Oops. There's a left click. As I right click, it's changing the type of trace, so that 45 degree bend or the 90 degree bend or the angle, the circular. So normally I'll just use, say, this 45 degree bend and just route the board. So as I move, it's showing you where do I have to end up connecting this to. If I hit the shift button, you can see it adds a via. So the type of via depends on, there's a setting up here, if I wanted a circular via or stuff like that. And when I reach a via, I could switch to the bottom layer if I so desired, like that. And so you'll need this if you had to go underneath a trace or something like that. You might need to go to the bottom layer. And this final one, I'll just route on the bottom to do something different. There we go. So you can check, there's a button over here that recalculates that rat's nest. And at the bottom, it says nothing to do, so that means all electrical connections are accounted for. So this means we have what we think is a completed circuit board. There's two more things to do. We're going to add some Silkscreen to it. So that Silkscreen was that extra stuff on top. By default, you'll see that it's telling you, where is it? So by default, it's going to print like that R1, R2, R3, R4. I could say, hey, I want to add some extra text on this. And so if you make one, make sure to add your name on it. And I'll just use the text command here. And I can write something. Colin is the greatest. And then for the text, we have to put it on. So Eagle has these different layers. So we already saw the top and bottom copper layer. Layer 21, T place, or 22, B place, is the top and bottom Silkscreen. So if I put it on the T place layer, the other thing we need to change is the font type. So Eagle has various font types. Vector fonts are the most reliable. Effectively, when it's written to the file, it has basically just this text without trying to have all the curves of the font itself. It tends to be the most reliable, so this is what a lot of people use. So I'll change it to vector and put that. And I could write something else on the bottom layer. We have both top and bottom Silkscreen on this board. You won't always, but for some of these fabs give you both, so it's nice. So if we put something else, we can put this on the bottom layer, and we'll see what this looks like in the 3D view. And you can see it's reversed. So whatever I wrote, because it's going to be on the bottom, and we want to read it from the bottom, it automatically mirrored that text for us. So that's just part of the sort of features it has in there. All right. So the final thing we need to do is remember what I mentioned about these design rules? We need to run a design rule check. So I've given you, in BB Learn, there's this Lab 6 extra files. And there's basically some files in a zip folder. And eventually you'll have to copy them over to your folder. One of those files is design rules. You don't actually need to copy them because the defaults are just fine. So I'm going to do that right now, though, so you need to figure out where you save that project. By default, it's in like this Eagle directory in your documents. And so I'm going to go back to my board and run, there's over here this design rule check button. And what this is going to do, it's going to do a whole bunch of checks. For example, it's checking the wires are not too close together, they're not too narrow or stuff like that. It checks how many layers there are. It checks what the minimum drill size is, so the holes aren't too small. So I just hit this check button, and it automatically, if there's errors, it comes up with a little window here and says, hey, error drill size. So in this case, it's saying, hey, your drill is too small based on what you told me the minimum size was. So you would have to modify that for the fab, or you can load the file. In this case, I'm going to change the drill size. So I could right click on that. And oops, this is the, so if I type change drill, so these are various Eagle commands for changing things. So by default, it's like 0.6 millimeter. I'm going to change it to 0.8. So these vias you can see enlarge slightly. And we can rerun the DRC. And nothing came up. At the bottom, you might not be able to see, but it says DRC no error. So that's good. One thing that sort of the real errors that you want to watch out for is that if I was routing and I wasn't doing a very good job, maybe I crossed these. So I crossed over some lines here. This will create an electrical short. When I run the DRC, it's actually going to flag that. So it's going to say, hey, there's an error. Your traces are too close together because they're overlapping. And in this case, it also flags that, hey, they overlap completely. So the clearance and overlap are obviously very, very bad. Normally it means you did something horrible like that. Or you simply put two lines too close together. So I'm just going to use this board as is, and we'll roll with it. So no errors. As I mentioned, you might get overlap, so you can go through. All right, so the final thing, now we can generate Gerber files. There's a little button here that looks like a camera, and this is the cam processor. So this generates the data that your PCB fab can use. Once it opens, you basically have to hit open job. In that zip file, there's this :gerb274x. So this file has some settings, some configuration that will make it easy for submitting your files to online fabs. So we'll run that. And again, you've got to figure out where the heck it saved it. So in this case, remember, I went to where my Eagle project is, the lecture demo. It defaults somewhere else, so make sure you get the right file. And I'm just going to hit process job. So all this is doing is this is copying some of your Eagle data to a separate file. So for stuff like the bottom, or where's the top copper? The top copper layer, for example, is all your copper information. It's going to copy stuff like the pads, the vias, the actual routing information, all to one file. And by default, it dumps them all wherever your Eagle file is saved, so that's sort of annoying. One of those 3 files in the zip file you downloaded from EVlearn is this movegerbers.bat, so I'm just going to run that. In my case, it stops it from running, so I've just got to say unblock. And all this does is it moves all the files. You can look at, it's just a batch file, so it's just running a few commands. It just dumped them all in this one directory. So this allows us to actually open them with a Gerber viewer, because these files include everything a manufacturer needs to build their boards. In addition, there's 2 extra files here I didn't talk about. There's this top stencil and bottom stencil, so not Silkscreen. Be careful of the names. I'm just going to delete them. What those are for is if you have a stencil made, and a stencil is like this little piece of metal or capped on tape or something, and it has cutouts for some of these devices, and it helps you apply solder to the board. In your case, you don't need them, so you can just delete them. Because sometimes it'll mess up one of the Gerber viewers. All right, there we go. So we did that. We generated the Gerbers. We moved them over. And we end up with a whole bunch of them in a directory. So we can use one of the 2 different Gerber viewers. So I'm going to try the 3D one. it doesn't always work on this computer, but you can drop Gerber files into it, and it'll take a second and should give you a view of the board. So now we have a 3D view of the board, so we can see where the copper is. The holes didn't show up. There's a formatting error, it doesn't matter for this viewer. You can see the Silkscreen on the top and flip it over, and the Silkscreen on the bottom. So it's a pretty nice way to sort of get a 3D view of what your board should look like and check anything crazy didn't happen. If that one doesn't work, the other option, the sort of more classic Gerber viewer, is something like Gerber V. There's a few others too, so you can search and find them. If I open all the Gerbers, so I'm just going to say open all. Basically what you see is this is all the layers are overlaid, so it's not 3D or anything like that, but in the checkboxes here we can look and say, you know, what is the top copper? So this is, all of this will be copper material. On top of this we can say all of this will be just the Silkscreen. So you can sort of get a view of what your finished board will look like. If I try to turn on the drill layer, so there's this NC drill, this numerically controlled drill, you should see holes, but what you notice is you don't see them. And this is one example where the file format information was wrong. So the default file format output from Eagle changed, and we have to increase. So it used to be auto detect. It auto detects the units and stuff okay, but I've got to say it has 5 digits instead of 4. So this is one of those annoying automatic things. And what we see now is that if I just look at that NC drill, you can see these drill hits. So this is the locations of drills and the size of them. So they're going to be drilled through the holes. So that's purely an artifact of this viewer. It doesn't. When you send it to the manufacturer, they'll detect that and fix the problem as well. But if you go to view it, it's nice to confirm that all the drills are where you expect them to be. All right. So that's how you view them. All right. So finally, we get to the point where you might want to order actual circuit boards. And this can be done pretty cheaply. So there's a few options. AP Circuits, which is in Calgary, by default, I think you get at least 2 copies of each board. For student projects, they'll offer discounts, normally like $500 a credit. You just have to pay for shipping. It's extremely fast. You can have a board back to you the next day. If you submit it in the morning, they'll do it the same day, ship it overnight to you, and at not an extreme cost. Or you can get it in a few days for a reasonable cost. If you have more time, sort of the classic ones that people are using are these other fabs. OSH Park is a very popular one. You get 3 copies of each board, and it's, I think, about $5 per square inch. So if you have a very small board that's like 1 or 2 square inches, which is like 1 inch by 1 inch, it's like, it could be $5 or less. That includes shipping to Canada and everything. It has a very user-friendly order process, so this is nice. It's going to show you what the board will look like before you order. Another option is something like there's a separate website set up, dirtypcbs.com, that I like, and they ship out of China, so it takes a little longer. You can pay for faster shipping, but you get 10 copies of each board, and 5 by 5 centimeters. This is like $14 American. And this is like $25 for 10 copies with shipping. So it's very, very cheap, and it also is user-friendly order process. So all you would do if you're interested in it is if you go to one of their websites. So they're all very similar. This one is extremely easy to use, which is why I like it. You basically can just select a file, and I would have to either upload my Eagle board file, or all these Gerbers I would just zip together. And then upload this Gerber file to it. And I can say, okay, open, and you can choose, you know, what's the size of the board. So it's below 5 by 5. You have to know the size of it. It's a 4 by 4 board in this case, so it would be 14 bucks. And you can select the board thickness. Default boards are actually 1.6 millimeters. This would be the normal board you get. And some of the other options too. So you can choose the color of the solder mask. They don't charge you extra for any colors. And again, it's always 14 bucks. So it's a pretty good way, if you're interested in testing out some circuit boards, to do that. As a warning, there's a few companies that will offer free design software. So they say, oh, download our free, so you don't need to learn Eagle. Download our free design software and order boards through us. Their software can almost never export this standard Gerber file format, so they lock you into ordering boards from their website. And their boards are a lot more expensive than any other option. So I know it's happened before where students have done the design, and then Mark's had to order them, and it's like $200 for these 2 circuit boards that would have been, you know, 20 bucks or something. So it's a lot nicer to use generic software like Eagle or another one, as long as it can output these Gerber files. So that's the real key thing to always double check, is it can output that, and then you can order the boards from anywhere. All right, one more bonus thing. If you want to order parts, so some parts you can get from Mark, you're going to run into this issue where you say, hey, I need parts either for my own project or something else. How do you go about doing that? So I'm using DigiKey. It's an online store that you can order any sort of parts from. I love DigiKey. They offer, it's $8 shipping to Canada, and they've had that for years, like 10 years they've offered that. If you call their 1-800 number, just someone answers right away. There's no like, press 1 for sales. And a lot of the times your orders ship, you'll place an order and you'll get an email like an hour or 2 later saying, oh, your order shipped. And it's probably gonna be there tomorrow. Maybe the next day after that, depending how lucky you get. But it's sort of 1 to 2 days, it's guaranteed to be there. So it's a really good company if you just need stuff right away. It's not very expensive, like the $8 shipping is insane. Inside them, this is some photos from the warehouse out of interest. So you can see they just have hundreds of thousands of components sometimes. So they just have these reels and reels and reels of components, and they have people that are picking them, placing them in your order. So somehow they get it all done in like an hour by the time you submit it. So the only reason I want to sort of take you through it is it can sometimes be overwhelming to find a component. So if you say like, I need a 1K resistor, let's search for resistor 1K. You end up with 42,000 hits on that. So it's saying, oh yeah, there's lots of 1K resistors. And a lot of these are garbage. So you've got to figure out, how do I choose? Now, there's too many options. I need one option that I can order. This is no good. So the first thing we would do is we would search down. It's going to have these lists of different types. So, you know, there's surface mount resistors. Well, if you don't want that, we can cross that out. Specialized resistors, we don't want that. And then finally, say, through-hole resistors. There's 11,000 matches. So that's still a lot. We're getting down, though. So the first thing we're going to do is we're going to check a box that says, only show me stuff you physically have in stock that you can just ship me right away. Otherwise, it's telling you stuff that it'll have to order in, which you don't care about. You don't need special stuff. So we hit in stock, apply filters, and then you end up with like 1,500. So still a lot, but it's getting down there. So let's narrow it down further. So they have this system where you basically have to go through and look at various options and just keep restricting your search until you get the resistor you want. So the first thing we would do is actually filter on a 1K value. So by default, it's matched some 1.2K and anything with 1K in the name. So we're going to filter on that, and we're going to filter on a 5% tolerance. So resistors all have a tolerance. If you go very low, so if you go like 0.01% tolerance, this is going to be very expensive. So it's not something you need. So 5% is quite good. So we would just filter on that. So this will give us like 100 options to choose from. So we're getting down there. So we're going to do a few more things. We could, and at this point, we just sort of have to look at these and say, what do I want to filter on? For example, this packaging option, I know, for a fact maybe that anything on tape and reel, this means you have like 5,000 or 10,000 of them you need to order. That's not what we want. We could filter on, what's the resistor made out of if we knew what we cared about. In this case, I know that the standard size resistor is like 1/4 watt. So that's how much power it can dissipate. We could filter on that. So I'll select that, add a filter, and we end up with a more reasonable count. So I think there's like 20 at this point. The final thing we're gonna do is we can enter the quantity that we want to order. By default, DigiKey is going to show you resistors that you have to order 5,000 of to even order any, which you don't want, I assume, maybe you want 5,000. So we would just put quantity 1, hit submit, and then it's going to sort it based on ordering a single resistor. And then the final thing we might do, so now it's given us, there's like 10 options that we can choose from. So we might finally have to say, okay, well, what's the package size? So we can see the length of the resistor. So some of them are like 6 millimeters long. That's sort of a normal length. Some are only 3 millimeters. These are a little smaller. So you would just have to look through and say, what is the difference between these 10 options? Is there anything I care about? Sometimes you don't care about the difference, so you just pick one randomly. In this case, we would choose a package and add it. As a note, if you're using DigiKey, there's a script that helps improve your filtering of the results of it. So you can download it. It just shows the pictures. So if you want to search by picture on resistors and stuff like that. I'll show you real quick. Let's see if I switch to DigiKey here. So very quickly, as an example, like if I wanted a 100 nanofarad capacitor, what would that look like? So I'd search for capacitor. And again, so it's giving me 354,000 options for a capacitor. So then we would have to narrow down what type of capacitor. If I knew it's 100 nanofarad, I might just say ceramic capacitor, which is the type like that's in your kit, the very small 100 nit style, small value. And as I said, the capacitance, so 100 nanofarad is 0.1 microfarad. So you can see it's going to give you different options for how it's presenting that data, but it's the same data. So how many 100 nanofarad capacitors do you have? 5,000 of them. So that's still too many. We'll again do the in-stock trick. And then see. So we're down to 3,000. So at this point, we just have to start looking at options that we know we want. One thing you would know is that you probably don't want surface mount. So some here under, you'll see mounting type. This is often what you'll see. There's an option for through hole. We just hit apply filters. So we're now down to 256. So we're getting there. And we can start to look at pictures too. So you can see the format, like something like that would be useful. There's going to be other styles that we might not want. So this would be a radial, I believe, is that called? Which is radial, which is axial? No, axial, sorry. So this would be an axial. Their leads come out at the end of the capacitor. We probably want them coming out like this, which is the radial style. So what we could do is we could filter on just radial packages. So you can see radial package case radial. So again, you've sort of just got to go through and see what's options to filter on. So we're down to 211. You could either, at this point, you may not care about too much else, so you could just pick one randomly. You could say, well, what's the voltage rating? I only need maybe 50 volts or 25 volts. This 1 kilovolt capacitor is going to be very expensive, so we don't want to get that. It would work for us. It would work perfectly fine for what you're doing, but we just want to get cheaper stuff. And finally, the tolerance. For capacitors, we're typically not so picky, so I'd go 10 or 20%. I'm going to avoid that really poor tolerance, the -20 plus 80, because those they don't have as high tolerance and normally as good temperature coefficient. So finally, I'm going to do this quantity 1 and then just pick something. And you could filter if you want. You can just say sort by price, because I'll pick the cheapest. So there you go, 32 cents. What you might care about is, for example, what's the spacing between these leads. So this is where you could get into more detail, especially if you're laying out a circuit board. You would care what the lead spacing is. In this case, this 0.1 inch, that's your standard spacing in your breadboard or anything like that. So that's convenient. So I'm just going to pick that and go with it. So that's really quickly the type of process you can use when you're selecting parts, and I could add as many as I want to the cart. So when you go through DigiKey, you'll almost always see this, that you're going to get far too many options. So if you just need a diode or LED, you'll get thousands and thousands of options. So you can just go through using the filters to narrow down to a selection of components that you care about. So basically with that, are there questions on the PCB, Eagle, or component ordering stuff? All right. If not, as I say, if you want to do the lab, the TA should be around today. I'll double check. It's not, there's no hand-in for it. It's entirely optional. If you do want to do it, I'll set up a submission system, or you can email to Mark. The eagle.brd, so this is the board file, by next Monday at 1 p.m. Basically, there's no real extensions because he needs to assemble them together and send them away. And if it takes too long, he won't have time to do that. So if you want to do it, you can do it in the lab now or later. It doesn't really matter when you do it, as long as it's in by that deadline. Oh yeah, when will you get them back? I don't know for sure. You can't use them in the robot. It won't be in time for that, and it's extra stuff anyway. Hopefully before the end of August, or before the end of July, possibly, sorry, I mean, definitely by the end of August. So if you're going away in September or something, it'll for sure be there by then. Depending how fast he's able to get it in and done, it could be as quick as sort of 2 weeks.